Okay. Hello. As you saw, I'm too soft. I don't want to have Shackleton in this video because he's like flaked out, fast asleep. When I film videos in this office, he always comes and sits on the chair next to me, and he's very keen video star, but he's it's a bit warm, and he's pretty flaked out. So anyway, I'm going to continue talking about this paper that just came out. So this is a paper. It's weakening, and I've talked about it quite a bit in the previous video, but it's by a whole bunch of authors from most of University of Alaska. Weakening of the cold halocline layer. Okay, so the halocline again is fresher water at the surface, very salty water deeper down, and a very sharp transition. That's called the halocline. And as the layer weakens, the warm water, warm Atlantic water from below the sea ice is coming up, and it's contributing to significant melt in the Arctic Ocean. And here's the warmer Atlantic water, warmer, saltier Atlantic water that's typically a couple hundred meters below the surface. You know, how it comes up through the Barents Sea into the Arctic and loops back here, loops back here, loops back here. So it's progressively moving eastward. And in this region here, it's starting to shoal and coming, instead of being a couple hundred meters down, it's about 60, 80 meters down, and it's starting to melt out the sea ice, keep these regions of the Arctic ice-free throughout the entire winter. So this is a very serious effect and feedback. They have all these mooring buoys here, and I'll show some of the data where I left off from the previous video. So basically, here's some of the key information. So if I go back to the moorings, if you look, mooring 1, M11, 3, 4, 5, 6. So as you go to higher numbers, you go further south along the Geckel Ridge. So we'll go back here, and this is water temperature. This is from the years 2014 to 2019. Okay, and this is temperature, and this is heat content, and these are the different regions, M14, 3, 2, and what you can see here, so you can see summer, winter, the warmer water going up to the surface, the heat content coming here, but the biggest change is in this station here. So you can see the extent of the heat, and then suddenly here it's coming right up to the surface. Okay, so the water temperature is increasing significantly right up to the surface here, and then the following year in the summer here. And in terms of the heat content, is coming right up to the surface. Okay, so this is the key. This is the key factor. So there are regions, and those mooring stations are detecting the Atlantic water is the warm, salty Atlantic water is shoaling, coming right up to the surface. A lot of that heat is starting to take out the sea ice in that region, so it'll stay gone year round. This is the temperature. So this is a function of year, and this is the temperature rise of this is at 250 meters, 200 meters, and 150 meters. Okay, so as you go deeper, right, you get warmer water, right? So this is the Atlantic water. So it's warmer as you go deeper because of the Atlantic water is warmer and saltier. So it's it weighs more than the fresher, colder water near the surface. But you can see that the temperature is rising here. The trend is a rise over time. It dropped here, and slight rise here. This is throughout the years. Okay, so what we're seeing, so generally, and this is 150 meter, the green. Okay, these are the temperature anomalies. So we're seeing how the temperature, the trend, okay, both in the Fram Strait and in the Eastern European Basin, and you can see the trend, 0.15 degrees Celsius per decade increase, the trend. Okay, and in the Fram Strait it's even larger. And this is the depth of the Halocline base at the M14 mooring. And you can see that it was starting to shoal, a drop here, and it's much higher here. Okay, so it's coming to within the 80 meters of the surface, in recent years. And this is extremely significant and extremely serious because it means that the sea ice won't form in those regions even in the depth of winter. This is another image showing the potential temperature from the M13 mooring, and you can see, this is, you go through the years and you can see how the shoaling is occurring here. Okay, this is where I got the 60 meters from. It's not quite 60 meters, but the heat is going right up very, very close to the surface in the most, recent time frame that this paper covered. This is heat. Q, heat increasing, heat flux increasing. So this is this is ice equivalent of melt. Okay, so more and more heat is moving to the surface, more and more melting is occurring. This is some more data here showing this is going from 2013 to 2018. Buoyancy, frequency, salinity. So the salinity, okay, lower at the surface, much higher here. Heat content, okay, so we're getting the heat going right up much closer to the surface. Okay, there's more data here, different regions. Again, showing, if you look at the general trend, we're getting upward motion, not so much here, but here definitely upward motion of that heat closer and closer to the surface, especially in the last few years. So the trend, 18.7 megawatts per meter squared per year, slightly neutral trend, slightly down, up and up in the different regions. So there is variation from region to region. Okay, and here, okay, so this is good. This schematic kind of shows what's going on. So historically, we would have ice here. Okay, we would have a surface mix layer. So basically, thinner. We had ice before, solid, and now we have much thinner ice, and it's mobile. It's moving. Okay, current conditions. So that's the first point. Then there's a warmer surface mixed layer, SML. Okay, this region here. Okay, and this region here is larger. So the water is warming in this region. Okay, then we have a weakening, a retreat of the cold halocline HC layer in 3. Okay, so this is the halocline layer here, and what you can see is it's getting smaller and smaller. Okay, the halocline is weakening, so this distance between here and here is decreasing. The currents are getting stronger. Okay, that's 3. 4, increased Atlantic water vertical heat flux, red arrows, and horizontal currents and their vertical shear, blue arrows. Okay, so there's there's a lot of vertical movement of water, of Atlantic water, which is the reddish at the bottom. The Atlantic water is shoaling. It's coming closer to the surface. So instead of only coming up to, shown here in this diagram, about 150 meters or so, right? It's now, it's moving upwards. Okay, so you can see the dashed line here is moving upwards. More heat is going upwards. There's more shear. So the difference in arrow lengths is less here. Here we get faster motion here. So there's more shear, and this shear causes turbulent mixing. So turbulent mixing is a big mechanism for bringing heat up, whereas before it was just something called double diffusion. We're getting replacement of double diffusion by shear instabilities, and this is as a fundamental mechanism of vertical flux, vertical motion of heat. So there's more and more heat coming from down below. This is happening on the eastern European Basin, and it's moving into the Arctic. So when it continues, when it's moved and completely covered the entire Arctic Ocean, then goodbye ice year-round, essentially, from what I can see. This is sort of the current speed, different locations. There's all kinds of plots here. Okay, but that's the key factors of this paper. So we're losing the halocline, the warm Atlantic waters coming up. And, one thing that they did say in this paper is they're saying in recent decades there's been a dramatic decline in seasonal sea ice extent in the Arctic Ocean, with a more recent year-round decline in sea ice extent area and volume. I disagreed with that, because look at the loss of sea ice is, at least in volume, is in all seasons, year-round, less and less ice. And we know now in the winter, and at the end of winter, it's the warmer water down below, heat coming up, that's causing the significant drop in the ice in the winter months. Okay, so another key paper on this topic is reduced efficiency of the Barents Sea cooling machine. So we can talk about, the Barents Sea, the dense water masses from the Barents Sea are very important for it says Arctic, but the Atlantic meridional overturning circulation. That whole water current system is key, because the main points where the water descended to feed the lower portions, the deep water portions of that conveyor belt system, occur in the Arctic. When the ice forms, it rejects brine. The brine is denser, sinks to the bottom, brings water down to the bottom, completing the loop of the AMOC, the Atlantic meridional overturning circulation system. But what's happening in the Barents Sea is a cooling machine, if you like. Warmer Atlantic inflow, there's less sea ice, there's more regional ocean heat loss. That's changed, so it's less efficient cooling. So there's less cooling of the water, and there's less descending water, therefore, in those chimneys, and this is slowing down the AMOC and will eventually likely stall it out. Okay, so this is very crucial connection of the global AMOC current system to the Arctic Ocean. The Arctic part is the Arctic thermohaline circulation. As the upstream Atlantic water freshens while it's still relatively warm, we speculate that the Barents Sea within a few years may export water masses of record low density to the adjacent basins and deep ocean circulation. In other words, the AMOC will get weaker and weaker and weaker. Okay, so this is an example here. This is a good image. This is the cold 1985 to 99 case, and this is the warm 2004 to 2018 case. This is Novaya Zemlya. This is Norway. Okay, so this is basically the idea. The Barents Sea, you get the water coming here, you get the ice margin here, you get the colder water, the brine pockets, and descending down into the abyss, driving the AMOC. But now as the ice retreats, there's less descending cold water. The water is warmer, and that cuts off the AMOC system. Okay, so we've got so the BS is Barents Sea, AO Arctic Ocean, Spitsbergen, Franz Josef Land, Bear Island Trough. These are all the different regions. But look at the yellow regions of heat. This is water temperature, and you can see that the warmer water is infiltrating further and further up into the Arctic region, and that will cut off the descending chimneys, if you like, of cold water, which feeds the thermohaline, the AMOC, the global thermohaline circulation system. So thanks once again for listening, and I will continue.